We've been talking now for couple of weeks now, I guess, about the fact that light is a wave. We talked about this earlier on, even before break, we talked about light being a wave. And ever since break, we've talked about interference, for example. Now, interference is an effect that is only possible with waves. Okay. Now, when I say that, what I mean is a wave as opposed to a particle. If I want to transfer energy to that wall there, I can yell at it, "Hey, wall!" Now, you didn't see the transfer of energy, but I transferred energy to the wall. My voice carries energy. The molecules in the air vibrate as my voice passes through it, and those vibrations go up against the wall, beat up against the wall, and a little bit of energy was transferred to the wall by my voice. That is transfer of energy by a wave. No one material particle made it from my mouth to the wall. No one material particle made it from me to the wall. All the waves in the medium of air vibrated back and forth. Individual air molecules vibrated, but they didn't travel. They vibrated in place. They didn't make the whole trip from me to the wall. No single material object made it from me to the wall. When I yell at the wall, yet I transferred energy to the wall through a wave. I can also take the top of this pin here and throw it at the wall and transfer energy to it. All right, well, give me a second. I got to retrieve that. When I throw the pin top at the wall, I transferred energy to the wall. But the pin top actually made the whole trip. This material object made the whole trip from me to the wall. I transferred energy through a particle. In the first case, a traveling wave carried the energy, and no single material particle made the trip. In the second case, I transferred energy to the wall, and a material particle made the trip. So you can transfer energy by a wave or by a particle. Both ways work. And they're different from each other. If two particles come together, they bounce off each other, like two billiard balls. If two waves pass one another, they interfere and then keep going. Interference is an effect that we saw that is the hallmark of waves. When you see interference, you know it's a wave. So interference is one thing we saw. We also talked briefly about diffraction. And back before the break, we talked about dispersion and rainbows. Okay? Light does all these things. It interferes, it diffracts, it disperses. So we know that light is a wave. There are certain experiments we can do, like Young's double slit experiment and like thin film interference, that show us conclusively that light is a wave. There is no way to interpret the results of those experiments, thin film interference and Young's double slit experiment, or even rainbows or diffraction. You cannot understand the results of those things without saying light is a wave. When you see interference, when you see diffraction, when you see dispersion, you know you've got a wave. Those are things that only waves do. Okay. Now, early in the 20th century, they kept doing experiments with light. They thought something was weird about light, couldn't quite figure out what it was. Certain results didn't make sense, like the ultraviolet catastrophe we talked about in videos 1 to 3. The black body radiation thing. That didn't really make sense. So people thought something was weird with light, but then it was discovered that sometimes light acts like a particle. Okay. Two experiments in particular. Experiment called the photoelectric effect. Photoelectric effect. Okay, was done early in the 20th century, and another one called the Compton effect. There are others, one having to do with X-rays and such. But the point I want to say here is that there are other experiments you can do with light. One of them is called the photoelectric effect, the other one's called the Compton effect. And the results of these experiments are not, they don't make any sense at all if you assume light's a wave, but they do make sense, and the only conclusion you can reach from these experiments is that light is a particle. Okay. So sometimes when you ask about the nature of light, the answer you get back from nature is wave. Sometimes when you ask about light through other kinds, I can't remember who said it, but somebody once said that an experiment is like asking nature a question. Okay? Young's double slit experiment is like asking nature, what's light like? The answer nature gives us is wave. Light is a wave. There's no other way to understand the results without postulating that light is a wave. The photoelectric effect is another experiment you can do, another way of asking nature the question, what's light like? And the answer given to us by the photoelectric effect, and there's no wiggle room around it, is that light is not a wave, but a particle. Okay? And the two are very different. The two are very different. Yet, there they are. Light is both a wave and a particle. Now, this is resolved, okay, this duality. This is known as the particle-wave duality, because light is both a wave and a particle, but it is resolved by a mid-20th century development known as quantum field theory. Now that is way beyond the scope. That's the sort of thing you learn in advanced quantum mechanics in graduate school. So we're not going to get into that, but the point is that it is resolved. Okay. From our point of view, it seems like it's an impossibility to resolve the two. Okay, and historically it was quite a conundrum. And so what I want to say here is that the one thing that what I want to leave you with is that these experiments that show that light is a particle also demonstrate what solved the problem with black body radiation, the so-called ultraviolet catastrophe, which is that we, again, are driven to the same conclusion that light is a particle with energy given by Planck's constant times its frequency. Now, right there, you see the particle-wave duality, because we're saying that light is a particle, or a quantum, a packet of energy E given by HF, but F is a frequency. How can a particle have a frequency? That's exactly what we're talking about. Okay, how that can be. But both of these lead us to the same conclusion that we were driven to by the study of black body radiation. That light has an energy of H times F, where F is the frequency. Okay, and so light is a particle as well as a wave. A particle of light, you know what it's called? Particle of light is known as a photon. And it has the symbol gamma. So we see gamma in a particle physics book, or any physics book, for the most part, it almost always refers to a photon. Okay? Particle, it's massless. Put your mind around that one, and travels at the speed of light. Okay, with energy, HF. All right, we'll pick up here and move on to the next issue, next topic under particle wave duality, which is even cooler.